Ah, okay lang, working holiday.
Working po.
Sa bahay lang naman eh. So, yeah.
So,
Really avoiding going out. The Omicron variant is quite troubling, but I really hope. Ano po
nga
ba?
po eh.
Oo nga
Binita
eh.
ni Joshua may papaswab daw siya tomorrow dahil may fever and body pains po daw siya.
Joshua right now?
Yung pong isang teacher niya rin po.
Oh, okay. Oo nga eh. But I really hope.
Parang
Ano dun
nag-post po
kasi?
yata sila. They went to somewhere to a resort or something.
Yeah.
Relatives.
Oh, which is understandable then. Um, it's really frustrating that this variant mutated, or rather was allowed to mutate. So, see, Josh, are you old enough to be vaccinated?
Yes po.
Joshua?
He turned 12
Okay,
last
okay.
15 po. So, two doses na siya. Kaya, first time kami nakipag-join din sa mga immediate
Okay, all right. Okay, that's reassuring. At least ano siya. And then the booster naman for Joshua, or wait, I don't know if boosters are available to minors. I think above 18 but at least Joshua is young, so if it happens, mas kakayanin. And again, hopefully nga, it's gonna be mild. Okay, kayo po sa sir, nagkapag-booster kayo or just the 2 doses?
nakapag-booster na po. Kaya talagang first time kami yung
Oh
kuya ko,
yeah.
he contracted the COVID last year. So medyo takot kami. Kaya ngayon lang, first time kami nakipag-join sa kanila. First time na nakita si Joshua eh. Sabi nila, lumaki na
After
pala
a long time.
almost 2 years po eh.
Especially at that age po, no? Ang bilis ng paglaki. So hindi mo makita for 2 years, noticeable nung paglaki eh. Hindi nang kunwari kapag 23 going on 25 years old, hindi mo mahahalata eh.
Opo.
Pero at that age, nung pagtangkad po, no, kitang-kita.
Tapos nakakapag-join na sila sa yung mga kapatid kasi ng mga siblings ko, ako po yung bunso. So na sila, late 20s na po. Kaya first time lang nila makipaglaro kay Joshua. Dati kasi masyadong malaking age gap.
Right. So ito, na. I mean, well, the age gap is the same, but well, parang hindi na sobrang batang tignan si Joshua ngayon.
Opo. Actually, he's taller than one of his yung cousins na married na.
Magta-transition na yan. All right. Anyway, so I'm really happy to see both of you again. Joshua, I was thinking of continuing with mathematical induction because there are so many other statements that we can prove by mathematical induction. Why did I decide to do mathematical induction at this stage? Kasi may mga iniisip na ako ibang topics to discuss. Meron akong gusto i-discuss sa trigonometry. So marami yon. And actually, we haven't really discussed anything yet from geometry even, not by much. All right, but I wanted to do mathematical induction and proving techniques so that, kunwari, meron tayong ipoprove sa geometry or sa trigonometry using math induction, then I wouldn't have to introduce mathematical induction anymore kasi ito nga, ginagawa na natin. All right, so I would really like to consider this as one of the basics. Tapos, given your level of aptitude, it is apparent that we don't have to go through the mga basics. Like, for example, we don't have to talk about how to square a binomial, how to multiply polynomials. So I am assuming that the basic stuff you already know how to do, but at any time that there is an assumption I'm making. So, kunwari Joshua, I might end up assuming, siguro Joshua, malamang alam mo na to. But if it turns out na hindi mo pala talaga alam, don't hesitate to let me know. Okay? Na-imagine ko kasi baka mahiya ka sabihin, baka kasi mag-assume ako na dapat alam mo, yun pala hindi mo alam. Tapos isipin mo, ay naku, dapat alam ko kasi inassume ni sir na alam ko. Okay lang yun. Alright? I would really rather i-discuss natin. Okay. So mathematical induction is a proving technique of proving a statement which involves non-negative integers. So n start greater than or equal to 1, or so sometimes even when n starts at 0. So I illustrated mathematical induction to prove the sum of the first n squares is given by that same formula, n plus 1, 2n plus 1 over 6. And I also used math induction to prove a statement involving divisibility. 4 to the 3n plus 1 plus 2 to the 3n plus 1 plus 1 is divisible by 7 for all positive integers n. So when n is replaced by 1 or by 2 or by 3, so it turns out that that expression there with the 4 to the 3n plus 1 plus 2 to the 3n plus 1 plus 1, it's going to be divisible by 7. All right, so I placed here statements that when you find the time, I'd like you to write down your ideas, your proof using mathematical induction. On top of that, there are... Yes, Joshua?
Para po siyang proof recursion. You will prove na you can go kumbaga from the next step po. And then if you can go from the next step, it means you can go all the way up.
Yeah. Oh, so that's the idea. Oh, but again, so that will make up the bulk of the solution. But we should always not forget that there's a first part. So prove that the statement is true for the first value of n. So when n is 1, or sometimes when n is equal to 0. So from level n, you could go to level n plus 1, but let's make sure that we can actually make the first step. Okay, so there are a lot of other statements that we can prove via mathematical induction. So for better organization, January 2022, let me turn this into December 2021. Okay, so go ahead, dito na page. Yeah. January. Or today is Tuesday. All right. Okay. Parang gusto kong tanggalin ng mga years dito for uniformity. But anyway, sige, saka na yan. January 4. Sa mga equations. Ito. Continuation of math induction. Example. Prove that 2 to the n is less than n factorial for integers n greater than or equal to 4. Okay, so the claim that we are trying to prove here is this. So ito nung p sub n. So remember what is p sub n? Using the examples that we looked at previously, p sub n is the statement that we are trying to prove, and it's a statement depending on the positive integer n. So the divisibility by 7 of that expression, that entire thing is a statement p sub n. Now, in the examples that we looked at, we were trying to prove that p sub n is true for all integers n starting from 1. But sometimes it may happen that the statement is to be proved only for integers n starting not at 1, but at some other higher level. And that's because if you look at p sub 1, p sub 2, and p sub 3, you can see that they're going to be false. P sub 1 is a statement 2 to the first is less than 1 factorial. P sub 2 is a statement 2 squared is less than 2 factorial. P sub 3 is a statement 2 cubed is less than 3 factorial, all of which are false. So, of course, if a statement is false, there's no way we can prove it to be true because it is false. And it is easy to verify that these three statements are indeed false. So of course, we're not going to prove that. But even if we are making the claim for all integers n starting only at 4, we can still use math induction. We're just going to have to modify the first part. So instead of verifying the validity of the statement when n equals 1, we're going to start verifying it for the case where n is equal to 4. So p sub 4.
Kumbaga po, you can climb the first 3 steps of the stairs. But you can climb from the 4th step. Kumbaga, you just move the ano po. You just shift.
Yeah, Parang ano, ayaw mong akyatin ng 1, 2, and 3 because those steps of the ladder are dirty or slippery. So what you want to do is skip to the 4th level. All right. So p sub 4 is a statement 2 to the 4 less than 4 factorial, which is equivalent to 16 less than 24, which is true. All right, so basically you just point out p sub 4 is true. So now let's assume that p sub n is true. Suppose 2 to the n is indeed less than n factorial for some integer n greater than or equal to 4. And let me write down what our target is, what our goal is. We want to show p sub n plus 1 is true. In other words, 2 to the n plus 1 is less than n plus 1 factorial. All right. So we have our assumption ito. Okay, this is what we can use. What we can use. Tapos itong 2 to the n plus 1 less than n plus 1 factorial. This is what we have to prove. All right. Let me write down one argument. Okay. To prove that inequality, the last one, you could either start with the left side and then make an argument that, oh, 2 to the n plus 1 is less than this, in turn less than this, which in turn is less than n plus 1 factorial. All right, so that's one way of arguing. Or alternatively, you can start with the other side, n plus 1 factorial, and show that, oh, this is greater than this, which in turn is greater than this, which in turn is greater than 2 to the power n plus 1. Okay, so either method of attack is going to work. Now, because we are working with inequalities, what you put inside the intermediate steps will rely on creativity and insight. Because, for example, if you look at 2, I mean, we're really supposed to start with 2 to the n plus 1. All right. The thing is, there are so many things that are larger than 2. 2 is less than, you could write 4 there. You could write 5. You could write e. Ang dami mong pwedeng ilagay. So that's why we are going to have to be more careful. This is different than when, for example, we want to show that A is equal to B. Because it may take you many different steps to be able to conclude finally that A is equal to B. But what we are assured of is that whatever we put here and also here should be something that's equal to A. Pero kasi kung inequality ang what we are working with, there are many things that we can place inside those blanks. So anyway, let me illustrate one possible way of attack. Starting with 2 to the n plus 1. So what I'm going to do is I'm going to write this as 2 multiplied by 2 to the n. Of course, I could write 2 to the n plus 1 as 2 cubed multiplied by 2 raised to n minus 2. All right. But this is not going to be useful. Rather, because of the underlined statement in green, I want to produce, I want 2 to the power n to enter the picture. All right. Because I have something I can say about 2 to the n. 2 to the n is less than n factorial, and that means twice 2 to the n is less than twice n factorial. All right. Twice n factorial. So ngayon, kailangan na lang natin gawin, palabasin that twice n factorial, so dito na scratch work, is this less than n plus 1 factorial?
It's not equal to. Kasi kung equal din po square, it's still right.
Sorry, what's that?
Kung less than or equal to. Pero yung zero, gagana po yun.
Actually, pwedeng less than or equal to. Kasi if you have A less than B less than or equal to C, you still get to conclude that A is less than B strictly. Kasi you have the strict inequality symbol. So parang the bridge between inequality is broken between A and B. All right. But at any rate, 2 times n factorial is less than or equal to n plus 1 factorial, because n plus 1 factorial is n plus 1 multiplied by n factorial. So twice n factorial, is it less than n plus 1 times n factorial? Yes, that would be true, because you would need 2 to be less than n plus 1. And that would be true if n is greater than or equal to 1. But in fact, n is greater than or equal to 4. That's what we are assuming in part number 2. So here we could include this argument that twice n factorial, this is less than n plus 1 times n factorial. Tapos ilagay lang natin ng ng reason. Okay. This is true since n is greater than or equal to 4. So that means n plus 1 is greater than or equal to 5, and that's clearly strictly less than 2. All right, so now what do we have here? N plus 1 times n factorial, and there you have it, n plus 1 factorial. So we have been able to show that 2 to the n plus 1 is strictly less than n plus 1 factorial. All right, so let's just wrap this up cleanly. Therefore, 2 to the n is indeed less than n factorial for all integers n greater than or equal to 4. All right, any questions, Joshua? Okay. I'll just write it down quickly, but let's say you wanted to start with n plus 1 factorial in trying to justify the inequality that we are attempting to show. Ito, double underline. If you are going to start with n plus 1 factorial, then you would have to write this as n plus 1 times n factorial. So bakit gusto natin lumabas ng n factorial? Because in the assumption that we need to use n factorial makes an appearance. So we have to keep an eye out for what tool is available because we have to find a way of being able to use that. Okay. Prove that 1 plus n is less than 1 plus x to the power n is greater than 1 plus nx if x is greater than -1 for all integers n greater than or equal to 2. All right. Okay. So this time though, it might be a bit disconcerting because in the inequality that we are trying to prove, so ito nung p sub n. So that's p sub n. Well, x is, you can think of x as a constant, or rather, if you look at 1 plus x to the n and 1 plus nx, polynomial sila eh. So, but apparently we are not concerned about the specific value of x. For some reason, we just want x to be greater than -1. I'm anticipating there's a reason why x has to be larger than -1. All right, but we can convince ourselves. All right, p sub 1. Well, apparently it would have to be false because p sub 1 would be the statement 1 plus x to the first power is greater than 1 plus 1 times x. And this is clearly false. All right. Then if you look at p sub 2, well, we might as well do the verification here. All right. P sub 2 would be 1 plus x squared greater than 1 plus 2x if x is greater than -1.
There's a whole
Okay.
number po, ganun po yun. Essentially.
Ano yun? If?
Basically po, x is greater than -1 basically just means x is a whole number.
No. Pwedeng x is -0.5. So it doesn't have to be a whole number. Okay, n lang, it's just n that has to be an integer. But nothing was mentioned about x. The only thing mentioned about x is for it to be greater than -1. So yes, x can be 0, x can be 5, but x can also be -0.5. X can also be equal to pi. But at any rate, we are doing the induction on n, and n is taking only integer values. So mathematical induction can be done here. All right, you were gonna ask something?
Kapag hindi po siya integers, magiging uncountable na po yung infinity.
Kapag hindi integer ang x,
hindi na po all integers n, naging all real numbers n. Pwede ba po yung induction? Kasi inisip ko po kasi parang yung pa po may uncountable infinity, siguro ganun din po eh. Where do you even start?
yeah, but at any rate, kasi we are not gonna go into uncountable infinities because n is supposed to be a real number. Okay, so I suppose you were thinking about kunwari n is equal to 1.5.
Ano po yung next po ng step?
Okay, I mean, this might still be true. However, here's the thing. If we are going to consider values of n which are not integers, then we cannot prove that using induction. All right, so in that case, we may need to appeal to other methods So other ways of proving, baka gagamit ng calculus or some other special fact about inequalities. All right. So itong 1 plus x to the 1.5 greater than 1 plus 1.5x, perhaps it may be true or not, but that I don't know. At any rate, we cannot use induction in that situation. All right. So at least ito, we would just have to look at when n is 2, 3, 4, 5. Anyway, what is p sub 2? This is equivalent to 1 plus 2x plus x squared greater than 1 plus 2x So then, this needs to be which is equivalent to x squared greater than 0. However,
X can be 0.
Okay, x can be 0 so I think there actually
1 but cannot be 0.
So pwedeng ganun, sige gawin natin. If there is something flawed or wrong with this solution, if we're gonna include the possibility that x is equal to 0, dapat we should make this greater than or equal to. Or I guess pwede natin gawin, make the claim strict inequality, but so long as x is strictly greater than -1, but x is non-zero. Sige, yun ang gawin natin. Na nasa listahan ko lang to, and x is not equal to 0. Okay. Pero and this is true. All right. Okay. Second part. Okay. Suppose 1 plus x to the power n is indeed greater than 1 plus nx for all x greater than -1 with x not equal to 0. Okay, so let's write down what we want to show. We want to show that 1 plus x to the power n plus 1 is greater than 1 plus n plus 1 multiplied to x. For all x greater than -1, x not equal to 0. All right. So this is what we're going to be able to assume. So we want to be able to use that. And then this is what we want to be able to conclude. Okay. So 1 plus x raised to n plus 1. So which we could write as 1 plus x multiplied by 1 plus x to the power n, which I believe you understand why we are rewriting it in this way, because 1 plus x to the n. All right. Okay.
Let's say 1 plus x is equal to y. Then obviously you can say y to the n plus 1 is equal to y times y to the n.
Sorry, what's that?
Say po 1 plus x equals to y, then y to the n is equal to y times y to the n.
Oh, yeah. All right. Pero I think I just realized bakit natin kailangan ng x greater than -1. This means that 1 plus x is positive. All right. So hold on to that fact. So we know that 1 plus x to the n is greater than 1 plus nx. So what? And then?
It expects po the solution. Kumaga, it knows na you will have to go to 1 plus x at least 1. So it made an assumption. So you won't end up in the paradox that 1 plus x is negative.
Well, I guess there's that. But again, can you clarify that? I want to be okay. So what is the question? Why do you think we need 1 plus x to be strictly positive? So that's what I wrote in red. Why do you think 1 plus x has to be positive?
So if it's negative, let's say 1 plus x is negative, -1, for example. It can be anything anyway po. So n plus 1 is negative, there's negative. Oh, it still works. Something's not right. But then, wait lang. There's no conflict in the signs.
Oh, walang. So that's not the conflict. Pero ito na mangyayari. Ito, I'm gonna multiply 1 plus x to the n and 1 plus nx by 1 plus x.
Oh, in theory po, the sign the inequality
Sige.
sign. But
I think you got it.
But then in the question po, that's not the case. Kasi kung 1 plus x to the 1, yung dito po yung to show po, 1 plus x to the n plus 1 should be greater than po itong statement po sa right hand side. But then if say 1 plus x is negative, then mag-flip po yung sign.
Therefore, yes, that's it. That's it. And ayaw natin mag-flip ng sign. So that's why it is actually relevant. So this is still going to be a greater than symbol since 1 plus x is positive. All right. So lesson here is, not take the givens for granted. So I mean, there's got to be a reason where it's needed. So now we have 1 plus nx multiplied by 1 plus x. All right. And then let's continue. Kasi ito ginamit siya dito. Okay. And then we have where when you multiply, what we now have are just two binomials. So 1 plus the coefficient of x is you have nx plus x. So it's n plus 1 x plus n x squared. All right. However, n x squared. Okay. Since x is not equal to 0, then x squared is strictly positive. All right, well, n x squared will be strictly positive. So this will be strictly positive. So we're gonna end up with this being strictly greater than 1 plus n plus 1 multiplied to x. Okay. But actually, yes.
It's positive anyway.
Sorry, what's that?
You can just trash the nx squared because it's positive anyway. So therefore it must be.
But you know what? I just realized here, in this case, even if x was 0, then okay, the only thing we may be able to conclude here is that nx squared is, instead of being strictly positive, it may be greater than or equal to 0, making this inequality here, the last one, greater than or equal to 1 plus n plus 1 multiplied to x. Pero kasi, it's okay because we already have this strict inequality here. So because of that strict inequality, the left side is still just only going to be strictly greater than what we ended up having on the right side. Okay. But I think the only reason why the non-zero-ness of x was used is in T sub 2. Kasi dito natin nagamit. All right. Tapos, let me write down. Okay, may isa pa akong inequality. Of course, I'm gonna write down some items for you to try when you get the chance. Prove that 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus dot 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 plus 1 over the square root of n is greater than the square root of n. For all integers n greater than or equal to 2. So, ayan, meron tayong sum, meron din tayong inequality.
So, basically, just 1, square root of 1 over 1 plus square root of 2 over 2 plus square root of 3 over 3 plus square root of blah blah. And then square root of n over n.
Sige, check natin. Well, we're starting with n equal to 2 kasi ito nung p sub 1. Sorry, this is p sub n. Let's just check p sub 1. This is, of course, not necessary as far as the proof is concerned. All right? Pero it is satisfying to see bakit mali nung p sub 1. P sub 1 kasi will have the left side sum start at 1 and then end at 1 over the square root of 1, which is 1. All right, so there's just one term. The right side, the smaller side, is supposed to be the square root of 1. So P sub 1 would be the claim that 1 is strictly greater than itself, which is false. All right. P sub 2 is the statement 1 plus 1 over the square root of 2, which is greater than the square root of 2. All right. So I guess you could use a calculator to verify that the left-hand side is indeed greater than the square root of 2. But let's do it old school. Let's not use a calculator. Kunwari, in a contest or in an exam, you don't have a calculator. It should be possible. This inequality is equivalent to the following. Square root of 2 multiplied to 1 plus 1 over the square root of 2 greater than the square root of 2 multiplied to the square root of 2 equivalent to the square root of 2 plus 1 greater than 2, which is equivalent to the square root of 2 greater than 1, which is true.
So if this continues po, diba po, may square root of 3 times 1 plus square root of 1 over square root of 3. So there will always be a plus 1, and as all of the square roots of any square roots of any n for any integer nga po except 1, laging greater than 1. So
Sorry. Again. That's an argument in support of what?
So eventually po, if you check all of them po, let's say po, square root of 3 times 1 plus 1 over square root of 3. Eventually, it will just boil down to square root of n plus 1 is greater than n. And, yun lang. Oo nga na.
Can you write it down what you're trying to say? Mahirap sundan eh. Or if you could dictate, or do you want to write it down somewhere? Nabilaw ka na.
Okay. Ito ba? Kaya pala. May series.
Are we okay? Meron ka pang isusulat, or I can wait if you were gonna write something down, or okay ka na?
So, tinignan ko po ulit. So, parang po siyang square root of, yun lang. 1 plus 1 over square root of 3. editors. So, saan po yung OneNote? I can't write pala dito.
You can try. So, ano sa, wait, did you still have the, we could view it on a browser.
Screen share po. Dito po.
And then your co-host, you could display your browser. You could take over the share.
Dito po. So,
Alright.
the example na pero lagi ko nag
Shouldn't that be square on the right side, square root of 3 times square root of 3? All right.
So, ina-notice ko po kasi
I see. Lalabas that on the left side, you would have. That's large. Which means, actually, Joshua, you have a proof here which doesn't use induction. So this is correct, but that's because so you have.
it requires induction din po eh. I had to does it require? Actually, I can
So actually,
from the first na lang po without having to do any other.
So actually, in this case, you don't have to do induction. All right, but what we're gonna see, especially when we were solving some of those when we were proving some of those divisibility statements last time, pwede silang improved by induction. Let me write down your argument on OneNote so that it's all connected. So it's all collected there. All right. Yeah. So I'll write it down later, but let's finish the induction. Okay. Suppose 1 plus 1 over the square root of 2 plus 1 over, now let me put the plus dot dot dot. Is greater than the square root of n for an integer n greater than or equal to 2. So we want to show that 1 plus 1 over the square root of 2 plus dot 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 plus 1 over the square root of n plus 1 is greater than the square root of n plus 1. All right. In this statement that we have to show, let's start with the left side. Because there is a lot of action happening here. So, well, what we simply ought to do is isolate the last term, and then inside the parenthesis. So this would be up until 1 over the square root of n, because we know that this parenthetical expression is greater than the square root of n. So this is what we have, the square root of n plus 1 over the square root of n plus 1. So ultimately, it all boils down to showing, we want to show this, that the square root of n plus 1 over the square root of n plus 1, ultimately we want to show that this is greater than the square root of n plus 1. So for this, you can work backwards. All right, because this is the same as the square root of n with n plus 1 inside. Plus 1 is greater than n plus 1, which is equivalent to the square root of n plus 1 being greater than n.
That's square root of n
All right.
squared greater than n. So therefore
N squared plus n is greater than n squared. So which is true. All right, thus you just have to find a way of putting it into the expression that we have. I guess one way of doing that is ito. Square root of n plus 1, tapos square root of n plus 1 plus 1, and then I'm going to use what we just saw here. Now, n squared plus n is strictly larger than n squared. So this is scratch. All right. Well, kasi n times n plus 1 is greater than n times n. All right. So this is what we have. This is greater than the square root of n times n plus 1 over the square root of n plus 1. So ang pinalitan natin would be, is that the square root of n times n plus 1 is strictly greater than the square root of n times n. And then this is n plus 1 equals n plus 1 over the square root of n plus 1, which in turn is equal to the square root of n plus 1. So there you go. This left side is strictly greater than the right side because this is the left side, and we ended up with that being strictly greater than the square root of n plus 1. So that wraps up the induction. So therefore, 1 plus 1 over the square root of 2 plus dot plus 1 over the square root of n is really greater than the square root of n for all integers n greater than or equal to 2. Let's write down your solution, which doesn't use induction. All right. No, the idea that you presented is the following: 1 plus 1 over the square root of 2 plus dot plus 1 over the square root of n. If you multiply the entire thing by the square root of n, so you would end up with the square root of n plus the square root of n over the square root of 2 plus the square root of n over the square root of 3. Ito for completeness, the square root of n over the square root of n minus 1 plus the square root of n over the square root of n. And what's going to happen is that the middle terms, they're all going to be strictly greater than 1. In fact, even the very first term will be greater than 1. The very last term will be exactly 1. But, well, that just goes to show that the sum that we have here on the right side is going to be strictly larger than 1 plus 1 plus 1 plus 1 plus 1 taken n times. So that's equal to n. So ito na nung what we have. Strictly greater than n. Ito. So our assumption here is that n is strictly greater than 1. So starting with 2, and then just divide by the square root of n. So there you go. You have the claim. All right. So that's a good find that you were able to do here. But Joshua, in this solution, which doesn't use induction, we were able to prove the statement, but we saw that the statement is false when n is equal to 1. Because if n is equal to 1, the left side isn't going to be strictly larger than the right side. They would be equal. So where do you think does the argument break down in this solution? Why does n have to be at least 2? Why is this solution going to be false if n is equal to 1?
Kasi po dito po sa so dito po sa kahit sa first step nga po eh. So I assume po na square root of n over square root of 2 is also going to be greater than 1. And that's true po for all of the numbers greater than or equal to 2. But then if n is equal to 1, then it's just going to be 1 plus 1 over square root of 2. 1 over square root of 2 is obviously less than 1 po. Kasi 1 over something greater than 1.
Actually, if n is 1, we are not going to reach 1 over the square root of 2. Kasi the denominators reach only until the square root of n. In this case, the square root of 1.
1 plus, 1. So basically 1 is greater than 1. Oh, bro, sad.
So in that case, if n is 1, hindi mo makikita ng square root of 2 or the square root of 3. So this is where it's going to break down. If n is equal to 1, this encircled term is the only thing that we're going to have there. And because that's the only thing, we are going to have equality. In the claim kasi, we want a strict inequality, and the strict inequalities require that other than the encircled term in red, we ought to have all these other terms which are strictly larger than 1. So mangyayari, these would disappear if n is equal to 1. All right, so that's why if n is equal to 1, the left and right sides of the claim are actually equal rather than strictly greater than. All right. Let's prove by math induction statements involving sequences. Defined recursively. So the sequence a sub n is defined recursively as follows. A sub 1 equals 2, and then a sub n equals a sub n plus 1 equals half of a sub n plus 6. So it goes without saying here that n is an integer. All right, we wouldn't need to write it down anymore. So hindi na natin kailangan sabihin that, oh, n here is not going to be 3.5 or n here is not going to be pi. The subscripts n and n plus 1, they have to be positive integers. Okay, so this is for all integers n greater than or equal to 2.
Of course po may first login front term. Yun pa yung first ordinal number. Pero may mga iba po kasi, let's say, yung you will go before pa yung A1, usually may ginagawa po sila ng ano rin eh. Yung A0 rin po.
Actually, for any sequence, you could always revert. Pwede kang bumalik. So, kunwari, you could let like n be 0. So a sub 1 equals half of a0 plus 6. And then you know that a sub 1 equals 2. So 2 equals half of a0 plus 6. So then you could solve for a0. That's going to be negative 2. Tapos, in the equation, you can let n be negative 1. So a0 equals half of a negative 1 plus 6. And you know that a0 equals negative. So as long as you have this equation, you could actually generate the sequence not only forward, but also backwards. Okay, but typically when we're working with sequences, unless there's really a need for it, we just, you know, move forward. Okay, all right. So you have encountered the term, have you encountered the term recursively before?
Opo, parang Fibonacci sequence po. To generate the next, you will need to use the previous terms.
Right. You will need to know the previous values. For sequences, it is possible to determine a formula so that in order to find the value of a sub 100, because if you're going to use the recursive definition, you would have to know what a sub 99 is, for which you would have to know a sub 98 is. All right. So it's possible to figure things out. It's just it's going to be tedious. So it is possible to come up with a direct formula. A sub n pala is n plus 1 to the 4th power. So then if you want a sub 100, then that would just be 101 to the 4th power. And if you have an explicit formula like this, you wouldn't have to know what a sub 99 or a sub 99, a sub 98 are equal to. But finding the explicit formula is gonna require some work. But in some situations, you could prove properties of a sequence by using only the recursive definition. So ito, prove that the sequence is increasing and that a sub n is less than 6 for all n. All right, so there are actually two things that we need to prove here. So first, show that the sequence is increasing, and second, a sub n is less than 6. Ano ibig sabihin ng increasing? So that means a sub 1 is less than a sub 2, less than a sub 3, less than a sub 4, onwards. You could write down some of the first few terms. So we know that a sub 1 is equal to 2. Let's just familiarize ourselves with the sequence. A sub 2, on the other hand, is half of 2 plus 6. So that means a sub 2 is equal to 4. A sub 3 is half of 2 plus, 4 plus 6. So that means a sub 3 is equal to 5. One more. A sub 4 is half of, so at 5.5 na?
If n po is less than 6 for all n, does that mean po na yung graph niyo po parang you will approach 6?
Yes. And also furthermore, not necessarily, kasi what if ganito, but by graph I suppose you mean this, no? A sub 1. So the horizontal axis is for the values of n. 1, 2, 3, tapos ito ng a sub n. So a sub 1 equals 2. A sub 2 equals 4. Tapos kunwari, andito nung 6. Okay, so one possibility is that, all right, the dots are less than 6 and they're increasing, but who knows, maybe they're getting closer and closer to maybe hanggang 5.9 nung hinahabol nila rather than 6. All right, so kumbaga, the value 6 appears up there in the clouds, but it doesn't mean that 6 is the ceiling of the sequence. So maybe the ceiling is 5.9, or maybe the ceiling is 5.95. So pwedeng
is first above the point being approached. Above
sorry, what's that again? I just want to be sure. What did you say?
It just means po na 6 can be above or below po, above or equal to the ceiling po.
Yes, that's it. Oh yeah, because a lot of people would assume that 6 is the ceiling. Pero kasi, so suppose I were to replace this by 10, then everything that we would have proved here would still be correct. That a sub n will be less than 10. Kasi nga a sub n is less than 6. So naturally a sub n would in turn be less than 10. But of course, it doesn't mean that 10 is the ceiling. All right. There's a good chance 6 is the ceiling, but well, we don't know. Maybe the real ceiling is 5.95. All right. Okay. The first statement, the first claim number 1. So how do we convert the claim the sequence is increasing into something that we can prove by math induction? Here's how. Claim number 1 is the following: a sub n is less than a sub n plus 1 for all integers n greater than 1. All right. Kasi if n is 1, then you have a sub 1 less than a sub 2. And then if n is equal to 2, the claim means a sub 2 less than a sub 3. And if n is equal to 3, this claim number 1 implies a sub 3 is less than a sub 4. So with all these inequalities together going onwards, we are going to be able to conclude that the sequence is increasing. All right. So the verification, okay, a sub 1 less than a sub 2 is equivalent to the following: a sub 1 is 2, a sub 2 is 4, and this is true. All right. So ngayon, next, suppose, so ito ng induction talaga, suppose a sub n is less than a sub n plus 1 for an integer n. Okay. What do we have to show? We have to show that a sub n plus 1 is less than a sub n plus 2. Okay. So mukhang kailangan natin gamitin ng recursive formula. Let me write it down here on the right margin. A sub n plus 1 is 1/2 of a sub n plus 6. Let's start with the larger one. A sub n plus 2 is 1/2 of a sub n plus 1 plus 6. Kaso nga lang, So we want to show that this is larger than a sub n plus 1. This is equivalent to a sub n plus 1 plus 6 being larger than double a sub n plus 1. So is this true? Well, this is equivalent to 6 being larger than a sub n plus 1. However, mukhang kailangan natin unahin nung claim number 2. Ano?
Kasi if 6 is greater than en, then 6 is also greater than a to the n, en plus 1. Yun nga po yung sasabi niyo po, 6 is not the ceiling. Kung gano'n po.
So hindi necessarily ceiling, but it's just 6 is just, you know, one of the values up there. But anyway, kasi in showing that, well, actually this is just one way of showing that a sub n plus 2 is larger than a sub n plus 1. It appears that we may have to rely on the fact that a sub n plus 1 is less than 6. Now that would certainly be true if we have already justified the second claim, which says that all terms of the sequence are strictly less than 6. Well, if a sub n is less than 6 for all n, what's that saying? All terms are less than 6. So from that, it would follow a sub 100 is less than 6, a sub whatever subscript, a sub 3n is less than 6. In particular, a sub n plus 1 would be less than 6. All right. However, when we prove, we only use those statements that we have already justified or which we have already proved. So in a situation like this, one may decide to prove the claim first that a sub n is less than 6 for all integers n. Okay, so option, okay, prove claim 2 first. Okay, however, so I wanted to mention that to point out that sometimes when you're proving something, especially when you are in a situation where there are not just one claim or theorem that you have to prove, there might be a second. Sometimes it's not going to matter which of them you prove first, but in other situations, it would matter that you prove one of them before the others. And sometimes you're only going to realize that when you're actually doing the proof, when you're trying to figure out your argument. Okay. However, I will employ this other option. Okay. Prove without claim 2. All right. Because I just realized the following. Okay. So we know that a sub n is less than a sub n plus 1. Ito nung what we are allowed to assume. Okay. Here's what I'm gonna do. I'm gonna add 6 to both sides. Tama pa rin, right? Okay, addition property of inequalities. And then what I'm gonna do is I'm gonna multiply both sides by 1/2.
No.
It's not going to change the inequality because 1/2 is positive. But then if you look at the left side expression, that's a sub n plus 1 using the recursive definition of the sequence. But the larger right side, on the other hand, using the recursive definition inside the box, that is what makes up a sub n plus 2. And so we were able to produce the claim that we are intending to produce in claim number 1. All right. Therefore, a sub n is indeed less than a sub n plus 1 for all integers n greater than or equal to 1. In other words, the sequence is increasing. All right. Claim number 2, all terms of the sequence are less than 6. All right. The very first part, the verification, is easy because a sub 1 is equal to 2, and clearly that's less than 6. Tama ba? A sub 1 equals 2. Okay, let me write down the recursive formula here on the right side so I don't have to keep on scrolling up and down anymore. Second part. Suppose a sub n is less than 6 for some integer n greater than or equal to 1. This is what we have to show. We have to show that a sub n plus 1 is also less than 6. Right? But this is not going to take too long because from the recursive definition, this is half of a sub n plus 6. However, we have this assumption. So itong a sub n, this is going to be less than 6. And then when you add 6 and multiply by 1/2, 6. So a sub n plus 1 is indeed also less than 6. And we had to rely on the assumption that the previous term, a sub n, was also less than 6. All right, so therefore, okay, a sub n is less than 6 for all integers n greater than or equal to 1. Okay. So we have seen a lot of examples, and I should be writing down at the end some of the other statements which you should also try on your own. So I'll write down statements that can be proved by induction, which are inequalities, which are about sequences. But the thing is, marami pang iba that can be proved by induction, which do not fall under these mga algebraic na arguments. Okay, so maybe next time. What I would like to talk about is a variant. Hello, variant is not such a good word these days. I'd like to talk about strong induction versus ordinary induction. Ganito, let me write down ordinary induction. Okay, to prove the statement that P sub n is true for all integers n greater than or equal to 1. So the first part has been to verify P sub 1. Tapos the second part is to suppose P sub n, so verify P sub 1 is true. Part 2 has been assume P sub n is true for some integer n greater than or equal to 1. And then what we want to do is show that P sub n plus 1 is true. Okay. Sometimes ordinary induction is not enough, and we have to use what is referred to as strong induction.
Then there will be weak induction.
Ano yun?
There will be weak induction po.
Paparin ng ordinary induction. Yeah, as much as you could refer to that as weak induction. Kasi strong versus weak.
So if there's strong induction, why don't everyone just use strong induction? I mean, like.
Sorry, what's that?
Kumbaga may na-release na bagong TV. And then you still stick to the CRT pa yung cathode ray tube pa rin po. Why do you still use the cathode ray tube when there's already a
all right. Kasi the thing is, parang ganito eh. So strong here doesn't necessarily mean better. Strong here doesn't mean better. I mean strong versus weak. So words kasi are sometimes imprecise. They come with mga associations we make with them. But even with proving techniques, depending on the situation, some are better suited. And in a way, even if ordinary induction is simpler, sometimes simpler is better. So ultimately, parang I always talk about it when it comes to choosing universities. In the end, it depends on what is suitable for you. All right, anyway, let me talk about how different strong induction is from ordinary induction. And then we can see why in certain situations we need strong induction rather than ordinary induction. And by looking at these examples, we are going to realize that in some situations, ordinary induction is enough, that we don't need strong induction in some situations. In some situations, ordinary induction is more than enough. Okay, here's how strong induction works. Verify P sub 1 is true. So it's the same first part, but the second part is where the difference is going to be. Suppose P sub 1, P sub 2, P sub 3, onwards to P sub n are true for some integer n greater than or equal to 1. And then what we are supposed to do is to show that P sub n plus 1 is true. So the difference is in what we are going to assume as tools that we can use, the tools that we're going to make available for us in the second part to show that P sub n plus 1 is true. Let me present an example first. This time, this is going to involve the Fibonacci sequence. Let me look for example. Ano yun?
Ano nga po, tama po kayo nga na. Kumbaga po, may lumang laptop. All you have to do naman po is just to, kumbaga po, all you have to do is to delete a file. Why use yung talagang super strong, kumbaga po, gaming laptop gagamitin niyo po when all you need to do is delete the file.
Yeah. All right. So sometimes you don't need the nuclear option.
You just need to.
So could be that. It could be that. So kumbaga, use only what is necessary. Anyway, ultimately, these are just terms. In a lot of references, especially for high school textbooks, for pre-calculus, the most that they're able to do is illustrate ordinary or regular or weak induction. But there are some situations where strong induction is what you actually need. Hold on, sorry, hindi ko makita no. Wait. I wrote it somewhere. Hold on. I think I have it. Hold on, yeah. Start. Okay. If you want, pause mo lang muna, but it's up to you. Yeah, I wrote it somewhere in my notebook, and then I closed my notebook, so I can't find the page, but I have it somewhere. Hold on, there you are. Oh, okay. All right, found it, but it's not. It's not the Fibonacci sequence, but some other sequence. Anyway, I don't find it. I'm gonna write it down now. The sequence A sub n is defined recursively as follows. A sub 1 equals 1, A sub 2 equals 8, and then A sub n plus 2 equals A sub n plus 1 plus twice A sub n for all integers n greater than or equal to 1. So what we have here is a sequence defined recursively. From the recursive equation, to determine the value of a term, you have to use the two preceding terms, which is why it is not enough to know the value of A sub 1. Even if you know the value of A sub 1, you cannot determine the value of A sub 3 without knowing the value of A sub 2. So ito, the situation is, to be able to say something about a term of the sequence, it is not enough to look to what happened yesterday, but you have to draw upon what happened 2 days ago as well. So to determine A sub 9, you need not only A sub 8, but you have to go further back. You have to know A sub 7. Now for this sequence, it turns out that this is the explicit formula. Prove that A sub n is equal to 3 times 2 to the power n minus 1 plus twice negative 1 to the n for all integers n greater than or equal to 1. Ayun, no? So we have this neat fact that allows us to determine A sub 100 without knowing the values of A sub 99 and A sub 98. But of course, we're not just going to take it on face value. We have to show that this is true. So why is ordinary induction not enough? Okay. So we'll see. First, let's do the look at the verification. if n is, so what is our p sub n? This is the statement p sub n. Okay. P sub 1 is the claim a sub 1 is equal to that formula, but if n is equal to 1, three times 2 to the 1 minus 1 plus twice negative 1 to the first power. So that's going to give us 3 times 1, so 3, and then twice negative 1 minus 2, which is 1. And that is indeed the value of a sub 1. All right, so p sub 1 is true. Second, okay, here's what we are going to assume. Suppose, okay, a sub n is equal to 3 times 2 raised to n minus 1 plus twice negative 1 to the n, and a sub n plus 1 is equal to 3 times double n plus twice negative 1 raised to n plus 1. So actually, ang ina-assume natin dito, we are assuming p sub n and also p sub n plus 1. What we're going to do here, we're going to show that a sub n plus 2 is equal to 3 times 2 raised to n plus 1 plus double negative 1 raised to n plus 2. So we're going to try to show that p sub n plus 2 is true. So in a nutshell, this is what we are doing. To prove p sub n plus 2, we are going to assume not only the previous statement p sub n plus 1, but even the statement before that, p sub n. Now, I just realized that I'm not exactly following the notation that I wrote here in my notes for strong induction, but I hope you get the sense. You want to prove that a particular statement p sub n plus 1 is true. In ordinary induction, it would be enough to assume the previous statement. However, in strong induction, we may need to assume not just the previous statement, but also the preceding statement. So p sub n minus 1. So you may have to look two statements back. So I also understand that in part number 2, I wrote here the assumption of not just p sub n and p sub n minus 1, but all the way down to p sub 1. But, well, I just wrote that down for convenience, but you can replace this with or some or only some of these. The previous statement p sub n and a few others. Okay, you were gonna say something, or ituloy ko muna. Yeah, yes, what is it?
To know po the previous term, we need to know the previous term, and then all the way to E1 po. To P1 po. So,
Pero kasi, when we make these assumptions, we are not really proving them. We are just assuming that they are true. So kumbaga, ganito nung, in terms of the ladder analogy I've been using, how ordinary induction works is this. We need to show that we can climb onto the first rung, the first level, and the second part is to show that we can reach, is that if we are at a particular level, level n, then we can climb up to level n plus 1. But with strong induction, the ladder analogy would go like this. We can climb to the first rung, the first level, as we verify p sub 1 is true. And then the second part would take on the following different form. if we are able to climb any level before level n, then that would enable us to climb up to level n plus 1. So kumbaga, we are going to assume we are able to climb not just level n, but maybe we have to assume explicitly that we have to declare explicitly that I can climb level n minus 1 as well. Ito. Anyway, let's finish this. Okay. A sub n plus 2, using the recursive definition, is a sub n plus 1 plus twice a sub n. However, courtesy of statement p sub n plus 1, we are able to replace the first term with 3 times 2 to the n plus twice negative 1 raised to n plus 1. Now, if all that we are using is ordinary induction, in our attempt to show p sub n plus 2, we would only assume p sub n plus 1. However, this whole thing about induction is that actually you need, if necessary, you may assume as well the earlier statements. The term we are giving to the strategy is strong induction. If you need to assume some of the earlier statements, whichever of the earlier statements are needed, however, kung ano man ang kailangan. Kasi if all we're going to assume is p sub n plus 1, then we would only be able to make a replacement for the first term. However, we want to apply the same replacement on the second term, a sub n. So that's why we assumed as well statement p sub n, so that double a sub n is double 3 times 2 to the n minus 1 plus twice negative 1 to the n. All right. So what's going to follow now is just some algebra na lang. So 3 times 2 to the n plus twice negative 1 raised to n plus 1. Tapos when you distribute 2, you're going to have 3 times 2 to the n plus ito, when you distribute, that's going to be 4. That's negative 1 raised to the power n. So 6 times 2 to the n plus, let's factor out, negative 1 to the power n. So we would have twice negative 1 plus 4. 6 is 3 times 2. So we're keeping in mind our target, our goal, this statement p sub n plus 2. So we have 3 times 2 raised to n plus 1. The thing inside the brackets, that's positive 2. But negative 1 to the power n, that's the same as negative 1 raised to n plus 2. Because negative 1 squared is just 1 anyway. And then times 2. So that's it. We have succeeded in justifying, showing that, yeah, a sub n plus 2 is indeed equal to this. A sub n plus 2 is that particular expression. All right. So in difference, we need not nitpick about strong induction and weak induction as being radically different techniques. Distinction lang is in the second part, assume what you need to assume. Take whatever tool is needed. It's just that when you take only the preceding statement, that strategy is called ordinary induction. And then if you take more than the previous statement, maybe the statement preceding that, or maybe 3 statements preceding that, then we refer to that strategy as strong induction. So therefore, A sub n is, finally, let's just clean this up. 3 times 2 to the n minus 1 plus double negative 1 to the n for all integers n greater than or equal to 1. Okay, you still okay so far, Joshua? Have any questions? All right. Okay.
Some sort of there's sort of some sort of hybrid techniques po.
Or what's that?
Are there sort of like hybrid techniques po? Kasi po, kumbaga, strong induction na combined with deduction or contradiction. Meron pa pong ganun po.
Oh, always. But I think we need to get a good grounding, good foundations. Be really comfortable with the mga basic situations, basic examples. So I really want you to find the time to write down your solutions. Because so far I've been the one who is solving. Tapos, in case this is new to you, I also want to see how you write down your solutions. All right. So when you find the time, do write them down because I want to see so I could point out what can be refined in your solution. But in the remaining time, what I would be doing is I'd be giving you many different examples, some of which are some geometry facts. Of course, some of these geometry facts can be proved without math induction. Pero
naman po, more of logic po na kasi yung usually, yung algebra po morely on values, yung geometry logic po eh.
All logic talaga. So nung parang sometimes the solutions might feel out of this world. Alright, pero kasi kung mga computations lang, kaya mo na yun eh. Kaya mo na ng mga ganun eh. So, ito, hold on. Naghanap po ng example in geometry. All right. All right, sige. I might have time naman for other examples, but let me get started with this. Okay, prove that for any integer n greater than or equal to 1, that if a unit square
Okay.
Okay. Don't worry about the term L Trominos. Let me illustrate what it is. It's an L shape.
Squares po na ganyan.
Ano yan?
Tatlo pong squares, yun nga po.
Tatlong squares, so yes.
Screen share po.
Sorry, what's that?
Screen share po.
Oh, so you're familiar with that. Anyway, so basta that's referring to an L shape out of 3 unit squares. Let's familiarize ourselves with what the problem is asking us to do. So,
Ito nga po sir.
are you familiar with this? Have you seen this, Joshua? Sorry, is that what you said?
Tatry niyo po daw na i-solve.
Ano yan?
Tatry niyo po daw i-solve.
Oh, sige. All right. So, pause muna. Try mo muna. Okay.
Saan yung pala ako? Okay. So, basically po, yung problem yata po, if I was assuming I was being correct. Kasi, if this, it's not going to be, ano po, it's not going to be, if this piece po is going to be removed.
Mm-hmm.
Tapos, ito naman, mas malaki. Piece naman po is going to be, ito po can you tile yung remaining na part of the chest?
Mm-hmm.
Ito po yung sinasabi ko niya una. So, is it always possible? Okay po, so I will just erase all this part. I will just so pang 2 by 2 square, of course, it is obvious po if you remove this part, of course the L shape can tile the plane. If you remove this part again, then of course it will you can see the piece.
Mm-hmm.
So now if we have a bigger, assuming 4 by 4. We can turn this 4 by 4 thing into 2 by 2s.
All right.
So now we have 4 2 by 2s. So we know that we can tile this 2 by 2 if we remove this piece. And we also know we can tile this piece if we know this. If we can also tile this 2 by 2 if we remove this piece. We can also know that for this piece too. And of course, we also know we can tile for any possible. It can be for any possible place on this 2 by 2. It can be here. It can be here. Whatever. So if you can delete. So if you can see, there's these red shading marks. Tatanggal. The red shading marks, I'll just turn them black because I don't have any time to erase. They also form an L terminal.
Okay.
So essentially, we just tile the entire plane because we know this can be tiled, this can be tiled, this can be tiled, and this can be tiled. And you leave one square. So if we have a bigger 8 by 8, my drawing is very bad.
It's okay. Because say you're nagmamadali, so
Well,
but I can see what you mean.
It's extremely into ugly. It's a hurt my brain already. So I'll just use this, and then I'll just use that.
Sana if it's easy to grid, but I got what you mean.
Grid. Oh. Why did I do this? Oh, why? I realized how I could have not done that. Anyway, I'll just continue. I should have turned that blue. And then we have further divisions, which I'm assuming this will become even more ugly.
Kasi dapat naman yung color.
I mean,
Yung
so we can also again divide this into 4 quadrants. Square. And then we've seen in this 4x4, this previous 4x4, that we can tile it with this with one missing square. So assuming we can tile this missing square, we can tile this missing square, we can tile this missing square. And we can tile any square here. So we already proved po na for any 4x4, we can always tile it with these L shapes.
Yeah.
As long as there's one missing. So we can tile anything. And again, we can again tile this L shape with another domino. So if we can continue this until 16 by 16, and then we can go so forth until 2 to the n by 2 to the n squares. Then we can always divide it into quadrants, and we can always show na there will always be a middle domino and then some other square. So we can always fill this up, this tiny gap, and then there will always be this gap. And we already proved for all of the quadrants, you can always tile them up. So basically, this means po na this entire thing with one missing square can always be tiled by dominoes.
All right. I think you got the correct idea, but what I want you to do, Joshua, is to write down the argument in so you got the idea, but I want you to convey that in writing. Nung idea. Okay, it's not an exact science as you try to find your voice in how you write down your arguments. All right, but usually minsan sa college students, parang they may have the idea, and I appreciate that, but I want you to, so for example, you may have to write down para paano mo i-convey na what you're really doing. But I got what you mean, and it's correct. Actually, that's the idea behind the argument. That's the correct idea. So tama siya. So which means I'm not gonna write down the solution anymore because you have the correct idea.
Okay.
All right, good. Meron na tong isang ayun, fine. So I'm gonna move this to the end so that you're gonna have space to write down your solution when you get the chance. Ito.
The advantage. Ito ba yung advantage po ng digital over physical because you cannot copy paste the physical.
Yeah. Although it would also be nice if we could, talk to each other face to face.
Okay. Pero gagawa po ka ng contraption para i-copy paste mo.
Anyway, let me get started with writing down this. Consider all possible subsets of the set 1, 2, all the way to n, all possible non-empty subsets which do not contain any consecutive numbers. Prove that the sum of the squares of the products of all numbers
What? Okay. Possible sources of the set do not contain any consecutive oh, okay. Proof that the sum something.
Okay. Let's have an example.
What?
Okay, when n is equal to 3. So we're looking at, so the set is 1, 2, 3. Let's list down the possible subsets of 1, 2, 3, which do not contain any consecutive numbers. So we have 1. Tapos we also have 2, 3. Tapos of the sets with 2 elements, hindi pwede ang 1, 2 kasi 1 and 2 are consecutive numbers. 1, 3, okay, pwede. How about 2, 3? Hindi pwede kasi 2, 3 are consecutive. And then what about 1, 2, 3? Hindi pwede kasi, 1 and 2 consecutive. So these are the only 4 non-empty subsets which do not contain any consecutive numbers. Then prove that the sum of the squares of the products. So from the first set, well, there's only one term. So the product you get out of that is 1. The product we get out of the second set is 2. From the third set, 3. From the last set, 1 times 3, which is of course 3. And then the sum of the squares of the product. So what I listed down are the products. Let's square them. And then add. We get 1 plus 4, that's 5, plus 9 plus 9, 18 plus 5, that's 23, which is 3 plus 1 factorial minus 1, because n is 3. So prove that no matter what n is, this fact is true. You want to try with with n equal to 4?
N equals to 4. 1, 2, 3, 4. This gets exponentially larger.
Pero yeah, let me move this.
Binabang sobrang laki po. Sabihin, malaki po yung solution.
Tignan natin when n is equal to 4. So we have 1, 2, 3, 4. So we have 1, 2, 3, tapos 4. And then with 2 elements, 1, 3, 1, 4. Yeah, 2 elements. So 1, 3. So starting with 1, and then starting with 2, 2, 4. And then with 3 elements, actually, if you take anything, magkakaroon ka ng consecutive. Then with 4 elements, that's actually, it seems these are all. So I have 1 squared, 2 squared, 3 squared, 4 squared, 1 times 3, 3 squared, 4 squared, 8 squared. Ito. Can you tell me what this is?
There's a formula for this. Well, I'll just do it old school. 1 plus 4.
Yeah, that's what I'm doing also.
5, 9. Confusion. Wait a minute. Oh, there's no formula for this. 1, 2. Yeah. 1, 4, 5, 9, 14, 16, 16, 30, 39, 16, 55, and then 64. 119.
All right, 119, which is 120 minus 1, and 120 is a factorial. That's 5 factorial. So this is 4 plus 1 factorial
Whoever
minus
found
1.
How did they find this?
All right. Okay. So if we are going to use induction, I mean, the verification is easier. That's straightforward. So if we're gonna think about this, we have to think of the inductive step. So kunwari, you know that when n is equal to 3, you get 23. So we have to think, how can we use that to come up with 119, which is the result when n is equal to 4. If you look at these two illustrations, pinagkaiba lang naman nila, well, you have 1, 2, 3, and 1, 2, 3. Pero ito, merong nadagdag na 4. So in terms of subsets, okay, nung mga subsets kanina, 1, 2, 3, 1, 3, they have no consecutive numbers. It's no wonder we're still able to find them here. 1, 2, 3, 1, 3. All right. The sum that we got earlier, 23, is therefore also among the terms that we have to add when n is equal to 4, because kita natin ng 1, 2, 3, 1, 3 underlined in green. But when n is equal to 4, we have additional sets. What are those sets? 4, 1, 4, and 2, 4. So they are the sets which have 4 with them. Okay. So, kumbaga ang nangyari, we have nung 23 earlier from the sets 1, 2, 3, and 1, 3. Itong mga ito, they make up 23. Tapos, merong bago. So, what I suppose we have to do is figure out nung bago, ano nung sum nila. Kasi nung for n is equal to 4, some of the sets appearing in n is equal to 3. And itong formula na to, if we're going to prove by induction, we can assume this formula holds when n is equal to 3. So we could use that to justify where 23 is going to come from. But what we need to consider in addition is, ano nung magiging sum, what will be the new squared terms out of the sets where 4 is included.
If n po is equal to 1, it jumps to n equals 2. May madagdagan po na isang term. Tapos sa next month,
Oh,
So padami further terms.
Okay. Tingnan natin ano nung mga nadagdag dito. Well, these are sets containing 4. Pero kung tatanggalin natin ng 4, so merong so this is empty set union 4. Tapos this is 1 union 4. Tapos ito 2 union 4. Kasi if 4 is gonna be an element of these sets, then wala dapat ng 3. Kasi 3 is adjacent to 4. So ibig sabihin, itong mga blue sets,
They don't contain 3.
okay, dapat ano, 4 along with subsets, okay, which don't contain 3, and there are no neighbors.
Kanina po eh. Kasi wala naman, yung nadagdag po is 3 tsaka 1, 3. So wala naman po 2. Sa next naman, wala naman 4.
Okay. Pero if 3 is not contained and there are no neighbors, then this would be equivalent to doing the analysis for the set 1, 2. No consecutive neighbors. Tapos 3 is not included. So if 3 is not included, hanggang 2 lang tayo. Hanggang 2 lang tayo. Try natin when n is equal to 5. At least let's list down the subsets. Okay. 1, 2, 3, 4, 5. So ano nung so you have 1, 2, 3, 4. Pero ilalagay ko nung 5 dito, nung meron mga 5. So nung nasa second row, sila nung mga bago. Okay. 1, 2 is out. 1, 3, we already saw it earlier. 1, 4, we saw it earlier. 1, 5, bago. So ilalagay ko dito sa baba. And now, starting with 2. 2, 3, hindi pwede. 2, 4, nakita na natin kanina. 2, 5, bago. Okay. 3, 5 the next. So it's new. And then 4, 5, well, hindi pwede, may neighbors. So, okay, sets with 2 elements. How about sets with 3 elements? If we start with 1, 1, 3, 5.
Wala na pong iba.
Wala na iba. So actually, ito na lahat yun, di ba? All right. So itong nasa first row, these are from what we saw earlier. So we expect that the sum that we're gonna get out of these is 119. Kung nakita na natin kanina. Pero itong mga bago, these are 5 with well, the empty set. 5 with 1, 5 with 2, 5 with 3, 5 with 1, 3. Ayun, no, kung mapapansin mo, ano nung mga ano nung mga kasama ng 5? 1, 2, 3, and 1, 3. So these are the sets earlier from 1, 2, 3. Meaning, hindi kasama ang 4 because 4 is adjacent to 5. And furthermore, no neighbors. So the subsets of 1, 2, 3 which have no neighbors. So yun nga, 1, 2, and 3, and 1, 3. So we have 119. Pero kung titingnan mo so when you square, so ito you have 5 squared. Tapos ito 5 squared with 1 squared. So ito ng mga i-add, 5 squared times 2 squared. Kasi well, in this set 2, 5, so of course that's 10. All right. And 10 squared. That's 5 squared, 2 squared. Tapos 5 squared, 3 squared. And then 5 squared with 1 squared, 3 squared. But note that this extra term, you can factor out 5 squared. All of them will have 5 squared. Tapos you have 1 squared plus 2. Okay. Pero note that 5 squared is may 1. Nung 1 squared plus 2 squared plus 3 squared times 1 squared times 3 squared, ito nung ginamit natin kanina when n is equal to 3.
Oh.
Ito yun, di ba? 23. Kasi when n is equal to 3, di ba? We use the subsets of 1, 2, 3 where there are no neighbors. So ito nung 23. So check na natin. Lalabas, we now have 119 plus 5 squared, and then 1 plus 23.
25 is 100, 600. 600.
700.
Oh, what? 719, sorry. 720. Oh, yeah, 720 po nga na. What?
Oh, 720. 720 minus 1.
Oh,
So ano yan?
I found this. Had no other thing to do.
All right. Okay. So from what we have written down, we can now map out our strategy. All right. So nung verification part,
That's the move even lower, bro.
okay, if n is equal to 1, the only subset we get from 1 is 1, and the computed number is 1 squared, which is 2 minus 1, which is 1 plus 1 factorial minus 1. All right, next, suppose the claim is true for 1, 2, all the way to n, and 1, 2, onwards to n plus 1. Hold on, sorry. I just realized I may need to correct some of my solutions above. All right, I will write down the assumptions of the second part correctly here. Suppose the claim is true for 1, 2, all the way to n, and 1, 2, all the way to n plus 1 for some integer n greater than or equal to 1. So we want to show for the set 1, 2, n, n plus 1, n plus 2, we want to show that the computed number is, ano yun kanina, nung for n plus 1 factorial minus 1. So this time, if we're going to replace n by n plus 2, so the computed number should be n plus 3 factorial minus 1. Okay, so what we're going to do is, okay, group the subsets of 1, 2, all the way to n plus 2 into group the subsets of n plus 2 with no consecutive numbers into 2 categories. Those subsets which contain the last element n plus 2 and those which contain n plus 2. Those which do not contain n plus 2, and B, those which contain n plus 2. Okay, ito, baba pa natin.
Labanan todo na po.
Oh, kasi nga pag sobrang baba. All right, I suppose, let's hope that's enough. Okay. Those which do not contain n plus 2, okay, the computed result will be based on 1, 2, until n plus 1. So subsets from 1, 2, all the way to n plus 1, no consecutive numbers. And for that, we get, ano na makukuha natin? N plus 2 factorial minus 1. All right, those which contain n plus 2. Okay. These will be the set n plus 2. So, kumbaga, ito no, when n is equal to 5, so you have the set with a single element 5, tapos itong mga iba, where 5 is associated with 1, and then 2, and then 3, and then 1, 3, which are sets that we encountered earlier when we only had 1, 2, 3 to work with. So basta hindi kasama ng 4 kasi 4 is adjacent to 5. So ito, these will be the sets n plus 2 and 5 combined with sets from, sorry, not n plus 2,
Sets from
combined with,
I see. So basically, may ano po siya, magiging n plus 2 squared times what the sum of ano yung galing sa n po.
okay, so the sum is, or rather, let's call it the computed result. N plus 2 squared plus Now you have n plus 2 multiplied to the squares of products, when earlier we only had 1, 2 all the way to n. So that would be n plus 2 squared multiplied to, when the set was just 1, 2 all the way to n, the computed result is n plus 1 factorial minus 1. All right. So ano nung computed results natin, which we're supposed to add up ito. Let's see what that's going to give us. Computed result, the computed sum is then n plus 2 factorial minus 1 plus n plus 2 squared plus n plus 2 squared, and then n plus 1 factorial minus 1. Let's see. This will become, well, we have n plus 2 factorial minus 1 plus n plus 2 squared. 1 plus n plus 1 factorial minus 1. Oh, hey, that's fun. No, 1 and minus 1 will cancel each other, giving us, in the end, this will be just n plus 1 factorial with n plus 2 squared. Itong minus 1, ilagay na natin sa dulo kasi we want the final answer to have a minus 1. So ito yan, no, minus 1. Minus 1, and then we have n plus 2 factorial plus n plus 1. Actually, n plus 1 factorial, and then n plus 2 squared. So n plus 2 times n plus 2. Kasi itong n plus 1 factorial with n plus 2, that would be n plus 2 factorial. So from the first two terms, let's factor out n plus 2 factorial. 1 plus, meron pa tayong n plus 2. Minus 1. That will be n plus 2 factorial. The bracketed expression is n plus 3. N plus 2 factorial with n plus 3 is n plus 3 factorial minus 1, which is what we wanted the computed result to be.
Whoever first solved this and whoever found this spin.
Actually, I've seen mga problems like this where nangyayari, you're doing an analysis on sets, and then if you're gonna use induction, mangyayari kasi, magkakaroon ka ng additional element, in this case, n plus 2. So what you do is you consider how was the situation when you didn't have n plus 2 yet versus what is the situation now when you introduce this new element n plus 2. So that's what led us to grouping the subsets into these two categories, A and B. All right. I said I was gonna correct something. Meron akong i-correct. Kasi itong part number 2, we proved the claim for n plus 2, and then we had to rely on n and n plus 1. So kumbaga, in justifying improving p sub n plus 2, we had to rely on the two preceding statements. And so the consequence is that in the verification step, you need to provide justification not just for the first step, but for the first two steps. Okay? Kasi parang lumalabas in the second part, to be able to climb a particular level, you need to be able to start at the previous two levels. So to get to level 3, you have to show that you're able to step on levels 1 and 2. So if you're only going to show that you're able to step on level 1, that does not allow you to climb to level 3 unless you first verify and illustrate that you can clearly climb up to level 2. So idagdag natin yon. The only subsets we get from 1, 2 are 1 and 2. And the computed sum is 1 squared plus 2 squared, which is 5, which is 6 minus 1, which is 3 factorial. So 2 plus 1 factorial minus 1. So in the problems where strong induction was used, so as you can see in this example, that there's no need to label the method as strong induction, but if we're asked, we used math induction. Sorry, we used strong induction. Dito, so kasi to be able to make the conclusion about a sub n plus 2, we relied on the claim when the subscript is n plus 1 and also n. So ito, if n is equal to 2, so 3 times 2 raised to 2 minus 1 plus twice negative 1 squared, 3 times 2, 6, plus 2, which is 8, which is clearly a sub 2. All right. So that's all for today, Joshua. I'll write down statements when I get the chance, but don't forget the other pending items when you get the chance, okay?
I hope I understand. I understood that last problem well.
All right. All right, have a good day.
Thank you po, sir.
All right. See ya. Bye.
Bye-bye
Bye-bye
po.
po.
Mind blown.